In the last 2 years, we've seen industry leaders spending hundreds of millions to equip their staff with the best AI on the market. At the same time, they have understood that unreliable AI is worse than no AI at all. 42% of companies have cancelled their AI initiatives, and 72% struggle with data quality issues. And this year, we've even seen AI agents deleting production data. Still, managers trust AI engineers when they show excellent benchmark results. What they don't know is that often AI is used to measure the quality of AI, a technique called LLM as a judge. So, can we trust these metrics? And how good are the prompts used by the engineers? And will new models like OpenAI's GPT-5 improve evaluation accuracy and robustness? I have tested 3 different prompts, compared 4 models, and the winner was, even to me, a surprise. I'm Karsten Held, and my mission is to help you make the best decisions when building or buying AI tools. I support small, high-stakes teams who need to deliver quickly within large organizations. Join me on a quest for precision, deep insights, and world-class engineering. Welcome to this video. Let's start with the key findings. The main point that I want to make in this video is that yes, LLM as a judge works. You can use AI to measure the quality of AI. And surprisingly, the prompt that performed the best overall was a very simple one. No special prompt engineering skills needed to create this prompt. Everybody can do this. It identified 99% of correct answers in a sample dataset, with 80% of reproducibility. That means this type of prompt can be used in production. What also surprised me is that the rubric-based prompt, this is the one that we mostly use in production, was bad at scoring. Of course, it could identify the absolutely correct answers with score 5, but it was very bad at applying scores from 0 to 4 at all the partially correct answers. Another interesting finding was that with the simple prompt, GPT-4o still outperformed all of the other models, even GPT-5. GPT-5 only performed better with a complex prompt that uses a mathematical formula to calculate the score. And lastly, some advice to AI engineers. First one is that you should always include the question that led to a specific model output in your evaluation. Put it in the prompt that you are sending to the judge LLM. This gives the judge much more context, and it will be better at identifying correct answers. The second one is that you should calibrate your evaluation pipeline. I like to compare this to the introduction of a new radioactivity measurement device. You would first calibrate it, prove that it's working, then seal it, and then use it without modification. This video has 7 parts, so you can easily skip to the individual chapters. First, we try to understand the problem. Then I try to answer the question, what is a good evaluation prompt? Then I show you the experiment setup that I used to compare the 3 different evaluation prompt types. Then we'll have a look at the results to see which prompt was the most accurate one and which one was the most stable. Then we'll compare the models that I used to run the evaluation, for instance, GPT-4o versus GPT-5, 4o mini, and even GPT-4.1. Next, we'll have a look at the score distributions to answer the question, why is the recall rate sometimes so low? And lastly, I want to give you my main takeaways to craft really good evaluation prompts. So, 2 months ago, I joined an enterprise search project that is using a RAG architecture. RAG is spelled R-A-G and stands for Retrieval Augmented Generation. And this is the typical ChatGPT type of system. The user is asking a question, also called prompt. The system then takes this question, goes into one or many search databases, searches for relevant documents, extracts parts of these documents, also called chunks, then reads these chunks and comes up with the best possible answer. To measure the quality of the answers given by the system, the team decided to use an LLM as a judge. The way this works is that you have a high number of reference questions and reference answers. The questions are handcrafted, and the answers are usually given by domain experts who simply know the answer. Or, if you know the documents that have all the information, to answer a question completely, you can also generate the reference answers using AI. And at first I was a bit skeptical, because I know that if you give the same prompt to an LLM many times, it will always come up with slightly different answers, even if the temperature is close to zero. That means we are trying to use a probabilistic technology to get deterministic results. Now let's try to understand the problem first, which is how to measure AI answer quality in RAG systems. In this example, I have a question that asks for 5 world capitals and their cultural contributions. And the reference answer gives us 5 capitals and 5 contributions. The model output had all the 5 capitals, but only 3 of 5 contributions, which gives us a partial correctness of 80%. Now, if you have a machine learning background, you might come up with the idea to use classic machine learning metrics. The problem is that these are not semantic aware. That means the order of the words counts. For example, if we have the sentence, "The cat sits on the mat," which would be the reference answer, and the model output is, "On the mat sits the cat," this would give us a very low score, but actually the answer is correct. It's just the words that have moved. Another idea might be to use semantic similarity or BERT score developed by Google. In this case, we vectorize the reference answer and the model output, and we calculate the distance between both of them. But here we have the problem that this calculation does not consider the question. For example, if the question is, what is the name of the main Olympian god, and the reference answer is Zeus, but the model output is Jupiter, semantic similarity would give us a very low score, because Jupiter is a planet and Zeus is a name. But actually, this god had 2 names, and the planet was named after the name the Romans gave to the god, which is Jupiter. So Jupiter is a correct answer. It might not be absolutely correct, but it is almost correct. So it also would deserve a score of 4, which semantic similarity cannot give us. And that leaves us with the LLM as a judge. The basic idea is that you take the question, the reference answer, and the model output, give it to an LLM, and ask it, is the model output correct? This seems to be a very clever solution. It's easy to use, it's easy to scale, and it's flexible because you can adjust the prompt according to your needs. The problem, however, might be the high variability of LLMs. Just imagine, you are sending the prompt with the same reference and the same model output to the LLM, and each time you are getting a different score. So I ask myself, what is a good evaluation prompt? It should have 2 properties. One is it should be accurate. That means if we have answers that are correct or almost correct, it should find all of them. And 2, it should be reliable. That means for the same input, it should generate the same scores on each run. So here you see the 3 prompt types that I came up with. The first one is very simple. In this prompt, we are asking the LLM to compare the model output to the reference answer and give it a score from 1, which is completely incorrect, to 5, which is completely correct. But that raises the question, what about the scores between 1 and 5? Does the model know what a score 3 and what a score 4 is? The next prompt is using a mathematical scoring model. Here we are trying to match the facts and conclusions from the model output to the reference answer, and we are calculating a fact ratio and a conclusion ratio. And then, using a mathematical formula, we are calculating the score. And here we also have some problems. What if the model is not able to identify the facts and conclusions? And what if we have no conclusions in the reference answer? Do we need to change the formula? So this is also a bit tricky. The third type of prompt is the rubric scoring prompt. This is what most AI engineers use, and this is nothing I have invented. I simply looked it up on the internet. Here we give the model a number of instructions, and we ask the model to look for accuracy, completeness, and consistency. At the same time, it should look for errors and omissions and ambiguity and so on, and it should not focus on the length of the answer. This type of prompt is also quite useful if we don't have reference answers. In this case, we are changing the rubrics from accuracy, completeness, and consistency to groundedness, relevance, fluency, and coherence. And we are giving the model the question, the retrieved chunks from the relevant documents, and the model output. And we can still score the quality of the answers from 1 to 5. But to me, the open question is still, Are these instructions and rubrics really useful to compare two answers? Or are we maybe overcomplicating things a bit? Just imagine, you and somebody else, you are getting these instructions and I give you a reference answer and a model output. Will you and the other person come up with exactly the same score? I doubt it. Okay, so now let me walk you through the experiment setup. And if you want to see exactly how it's done, it's all in the OpenAI backend tools repository on GitHub in a file called testeviloperations.py. The first step was to create calibration questions. I decided to use a score from 0, which is completely unrelated and incorrect, to 5, which is completely correct. And I created 10 questions for each of the scores. That makes 60 total questions. And I decided that the minimum score for correctness should be 4. That gives us 20 answers that we regard as correct, which is 33.3%. 1/3 of all the questions are passes and 2/3 are fails. The second step is to actually decide on the 3 prompts and then to answer some basic questions like, should we include the questions into the evaluation? And I decided, yes, we definitely should include the questions. Then which model to choose? I started with GPT-4o, but then later I also compared it with GPT-4.1 and GPT-5 and o4 mini. And then I asked myself, what metrics should be optimized for? What is the goal of this whole experiment? I decided that pass-fail stability is probably the most important metric. You want the model to reliably apply the same scores to the same input. Then in step 3, I implemented everything as a script using OpenAI evaluations and a score model grader. Then let each prompt run 30 times over the calibration dataset and then calculated all the metrics that you see here. Now let's have a look at the prompts that I have used. This one is the very simple prompt. I tell the model that it is an expert evaluator for a QA system. I give the descriptions of the scores from 0 to 5. Then I ask the model to also give me a rationale. So why did it apply a score 0, 1, 2, 3, 4, 5? And then I give the model the input, which is the question, the reference answer, and the model output. The next idea was to use this very complex prompt with fact matching and a mathematical scoring model. So first I explain what facts are, what conclusions are, and then I give the model a formula how to calculate the score and also examples. So for each score, we have one example and how to calculate the score. The last prompt is the rubric-based prompt. In this case, I went to the LangChain OpenEvals repository on GitHub and copied the correctness prompt. This prompt has a couple of rubrics, and I included the input, which is the question, then the model output and the reference answer. And here are the results. You have the prompts as the rows and the metrics as the columns. We have 2 metrics for stability and 3 for performance. Let's start with pass-fail stability. What is this? This is the percentage of items that either pass or fail consistently over all of the 20 runs. In the first case, we have 52 of these items and only 8 of the items are unstable. The second one is called scoring stability. Here, we are measuring the percentage of all items that got the same score over all runs. So we are measuring how repeatable the model applies the same score to the same input. We can see that all the 3 prompts are performing quite well in terms of stability. 2 of them even close to 90% in the pass-fail metric. Now let's have a closer look at the performance metrics. These are calculated based on the confusion metrics, which we use to understand a model's ability to classify items in a sample dataset. In this case, we only have 2 classes, scores 4 and 5, which are passes, and scores lower than 4, which are fails. The first one is called accuracy, and it answers the question, out of all the scored items where the model decided either pass or fail, how many were actual passes and actual fails? In the first case, the first prompt identified 1,191 of the items as correct fails or passes. The math scoring model predicted 1,110 out of 1,200 items correctly as either passes or fails, and the LangChain correctness prompt identified 974 of 1,200 items correctly. The next metric is called precision. Here we only look at the predicted passes and calculate how many of these passes were actually correct. Let me give you an example. Let's say a prompt scored 10 items with scores 4 and 5, which makes them passes. But 2 of them actually have a score of 3, so they were wrong. That gives us a precision of 80%. And now let's say another prompt is scoring 20 items with either 4 or 5, which again makes them passes. But in this case, 4 of them have scores of 1, 2, or 3, which makes them fails. And again, we have the same precision ratio of 80%. And now you see why precision can be a bit misleading if you don't look at the actual numbers. The last metric, called recall, is the most important one for me, because it measures the prompt's ability to identify the 20 items in our calibration dataset that have either score 4 or 5. And in this case, it doesn't matter if it applies a score of 4 to an item that has originally 5 or the other way around. We just want the model to identify passes, and all of them. And we see that the simple scoring prompt has the highest recall rate, which makes it quite accurate. Out of the 400 items with scores 4 and 5, it identified 394. The mathematical scoring model prompt identified 365, and the LangChain correctness prompt identified 174 out of 400 actual passes. That's why we have a very low recall rate of 43%. Now you might be asking, 20 runs, is that really enough to calculate reliable metrics? And yes, you might be right. Maybe it's not enough. But please bear in mind, running these tests takes a lot of time. And it costs real money, because each of the scoring gives us a reasoning. You remember, we specifically asked for it. And each of these reasonings can be several thousand tokens long. So if you do the math and multiply 3 prompts times 20 runs times 60 items, you know we are in the millions of tokens used. So running 1 hour of intense evaluations can quickly cost you more than your monthly ChatGPT subscription. But of course, I wanted to be on the safe side, so I rerun the script and got very similar results. And as you can see, the complex formulaic scoring model prompt has a scoring stability problem. That is because even with the same input, each time it calculates the facts differently. So sometimes it comes up with 5 facts counted, sometimes with 6. And that causes this major scoring instability. So if you ask me, I wouldn't use this prompt in production with GPT-4o. After all of this evaluation effort, I wanted to see how the 3 prompt types perform in a real-world scenario using real answers from an existing RAG system. So I went back to one of the RAG systems I've built earlier this year, took our benchmark with 30 questions and reference answers and the model output, and let it rerun against the 3 prompts, which 20 runs each. And I remember back then I was not very happy with the evaluation stability, because each time we would rerun the evaluation with the same model output, we would get different scores. Sometimes 87%, sometimes 90%. Here the overall benchmark is lower, it's 67%, but the pass-fail stability is at least acceptable. We have 6 unstable items. That means during the 20 runs, 6 items flipped from pass to fail or from fail to pass. Okay, so now let's dig into another really interesting question, which is, how important is the judge model type? The results are really surprising. I would have expected GPT-5 to outperform GPT-4o with each type of prompt. But as we can see, only the complex scoring model prompt gets higher metrics with GPT-5. The other prompts perform worse with GPT-5. Here I let the test rerun against OpenAI's high-end reasoning model called O4 Mini, which spends much more tokens and much more time to answer each question than GPT-4o. The picture is very similar. We get better performance with the complex formulaic scoring model prompt, but the 2 other prompt types degrade in performance. And we have a very similar situation with GPT 4.1 that was advertised as the beta version of GPT-4o. So the question arises, what will we do when OpenAI will discontinue all these older models and replace them all with GPT-5? Will we have to accept this performance drop for our evaluation pipelines? I would say no. Given these findings, we see that we can switch from one prompt type to another without sacrificing accuracy or stability. But what we need is a reliable evaluation toolkit that we can use to prove that our prompt is still doing its job and it's producing reliable results. Do you remember that the LangChain rubric scoring correctness prompt had very low recall scores, sometimes below 50%? I wanted to know why. And I went to the OpenAI dashboard where we can see all the evaluations. I looked up the same question with the same model output in 2 different runs. On the left, you can see the question passing with a score of 4, and the reasoning is the model output is mostly correct, but not completely correct. And the other run gives the same model output a score of 3, and it says the response is logically consistent but incomplete. Incomplete and not completely correct. Well, this is almost the same. But why do we get a score of 3 one time and a score of 4 another time? So I had a look at the score distributions. On the left, you can see the LangChain correctness prompt and the number of scores it gave to the answers. And what we see is that the score of 4 is simply not used. Only one question in one run gets a score of 4. But in the test data that is used here, we constructed 10 questions that should get a score of 4. On the right side, you see the score distribution of the simple scoring prompt. This was the prompt with the overall best performance. And while it gets the 20 correct answers right, it has a peak at the score of 3, because it takes a lot of items with target scores from 0 to 2 and gives them scores of 3. Now let's have a look at the mathematical score model prompt, and we can see a score distribution that is much more like the one we would expect. But at the same time, we also see a high variability, and that's why this prompt performed less well. Now let's go back again to the score distribution of the LangChain correctness prompt on the left. The main reason why this prompt has a low recall ratio, that means it cannot find the 20 correct answers with scores 4 and 5, is because it does not know what a score of 4 means. The prompt is good at identifying completely correct answers and completely wrong answers, but it's bad at identifying almost correct answers. Now let's take the time for a short recap. The main takeaways are that with older models, you should use simpler prompts, because too many criteria cause unstable results. Then you should also be exhaustive in your prompt. Tell the model what each score means. Otherwise, the model will not use the score. It will simply don't know what a score of 4 is. Then include the question in the evaluation prompt. Sometimes the question decides whether an answer is correct or not. With the newer reasoning models, you can also start using complex score calculation prompts. Identifying facts and conclusions, for instance, worked much better with GPT-5 than with GPT-4o. Then take the time to think about calibration. Calibration is necessary to prove that your evaluation works. Once you have that, you can optimize for pass-fail stability, because you want prompts that reliably identify passes and fails each time you run them. And then, please, if you have unstable evaluation results, don't average them. It's much better to start measuring the volatility of your prompt and then improve the performance step by step by modifying the prompt. Once you have your calibration in place, you can then choose the best model for your prompt. What you want is an optimal model-prompt combination that produces the best stability and the best accuracy. Now, I hope I could convince you that using AI to measure the quality of AI makes a lot of sense. If you want to see how I did these tests, please have a look at my repository on GitHub. The link is in the video description. You can also copy and use my script as a blueprint to run your own evaluations. But please remember, think for yourself, test your assumptions, and stay in control. My name is Karsten Held. See you next time.